This video introduces the concept of how you predict using a model, starting with state space models. The previous videos introduced the main concepts underpinning predictive control and also argued that linear discrete models are a logical basis for any predictions. This video builds on that by saying, how do we actually form the predictions now that we know the model form? And our initial focus is going to be on simple state space models. It's implicit throughout this particular video that the system is multivariable, multi-input, multi-output, and so what you'll find is the dimensions are not stated except where it's possibly unclear. And you'll find that's quite common in the literature, that the dimensions are often left as implicit or being obvious in the context. What we said in the previous video then was that a common state space model is given by something like this, where x is the state, y is the output, u is the input, d is the disturbance. In this video series we're going to restrict ourselves to this form and assume for convenience that d equals 0, so that particular term is going to disappear. Now, if you happen to need it, you could introduce a notation that said something like we've got nx states, n subscript s, mu inputs and my outputs. You'll notice we haven't used nu and ny for the number of inputs and outputs because that notation is very commonly used in the predictive control literature to mean something else, so we best reserve it for the common usage. A basic concept then of how you predict. Well, implicitly discrete models are one step ahead prediction models. That is, if you give me the data at sample k, I can use my discrete model to find the data at sample k plus 1. You'll notice that here the discrete model in the state is written as xk plus 1 equals axk plus buk. So if given xk and uk, I can find k plus 1. I can obviously therefore find the output one sample ahead by writing yk plus 1 equals c xk plus 1 plus dk plus 1, and then where I've got this xk plus 1 here, I can substitute in from there, and then what I get is this: yk plus 1 equals c a xk plus cb uk plus dk plus 1. Now hopefully that was obvious to everybody, so I've done it fairly quickly. Now normally you would assume that a best guess of the disturbance is that it does not change, because the assumption on the disturbance is it's a slowly varying one. So if we assume that dk plus 1 equals dk, then when I do that and substitute that in there, you'll notice I can then cross that and write dk, which is what people will tend to do. Alright then, the one step ahead prediction can be used recursively to find an n step ahead prediction, and this is the common thing that people do in predictive control, and we'll go through it moderately slowly here so you can see how it works. Alright, first of all what I'm going to do is write down my state space model at lots of different samples. You'll see I've not changed anything apart from the subscript, so I've got xk plus 1 equals axk plus buk. xk plus 2 equals axk plus 1 plus buk plus 1, and so on down. xk plus 4 equals axk plus 3 plus buk plus 3. So you'll see there all I've done is write the model at lots of different sample instances, but nothing clever, no tricks, just the same model, just changing the subscript. Now over here I've written the same model again, but what I'm going to do now is say, alright, how do I find xk plus 2? What I'm going to do is use this model here, the one I'm just circling in blue, but notice that within that model there's an xk plus 1, and I'm going to take that xk plus 1 from the line above. And you'll notice that's all I've done here. You'll see I've written a, and then in this square brackets is xk plus 1. So I've written a times axk plus buk, and then added plus buk plus 1 on underneath. So I've used the first two equations in order to find a two-step ahead prediction. Why is it two-step ahead? Because you'll see I'm now getting xk plus 2 based upon xk, uk and uk plus 1. What happens then if I want to go to xk plus 3? Well, I can do the same trick. What I can do, I delete some of this so we can see what's going on. If I want to find xk plus 3, then the simple trick is to take this xk plus 2 here and put it in there. So I'm going to write, do that now. You'll see there we get xk plus 3 equals a times xk plus 2, and if you look at what's in here, you'll notice all I've done is move that xk plus 2 down into there. Now, that expression is quite complicated, but the key thing is, you'll see I've now got a 3-step ahead prediction because I've got xk plus 3 equals a, and within the brackets there's just an xk, because I've worked out the xk plus 2 in terms of xk and the xk plus 1 in terms of xk. I can do the same trick again. You'll see if I look at xk plus 3, I can plug that in to the prediction for xk plus 4, and if we do that, again you'll see if I put the square brackets around here, the bit within the brackets is just xk plus 3, again expressed in terms of xk and all the future inputs. So the key thing here is you'll notice we're solving the n step ahead predictions recursively. We use the model at sample k plus 1 to find xk plus 1. We use the model at sample xk plus 2 to find xk plus 2, but we then substitute in from the previous expression, and so on. Now if we expand all this out, simplify all the brackets, you'll find this is what you get. Xk plus 1 equals axk plus buk. Xk plus 2 equals a squared xk plus abuk plus buk plus 1. Xk plus 3 equals a cubed xk plus a squared buk plus abuk plus 1 plus buk plus 2, and so on. And you'll see there's clearly a pattern developing here, and what you should be able to do is use recursion or otherwise prove what the general pattern will be. We can now write down then a general expression for the n step ahead prediction, and that's this one here. So if I wanted xk plus n, you'll see it's a to the n times xk, a to the n minus 1b times uk, a to the n minus 2b times uk plus 1, and so on all the way down to b times uk plus n minus 1. And again, I hope the pattern is obvious there and you can easily prove it to yourself. If you wanted the system output, all we're going to do is use the fact that y equals cx plus d. So you'll notice what I do now is just substitute that in, and the only difference with the y is you'll see I've got a c term here, a c term here, and at the very end I've got this plus d. So that's relatively straightforward. Now, at the moment, this prediction is mixing up past and future data. So what we want to do is be a little bit more careful with our notation in order to distinguish between what is past data, which is known, and what is future data, which is part of our prediction. So it could be decision variable, or it could be something that we don't know that we want to decide. Now, within predictive control, there's a common notation using a double subscript for prediction to try and avoid confusion. So the way this subscript works is the first term determines the sample of the prediction. So how many steps ahead are you predicting? You know, is it k plus 3, k plus 4, and so on. Now the second number in the subscript denotes the sample at which the prediction was made. And so you'll see this double notation only where a variable is in the future. So here's an example. If I write xk plus 4 slash k, what that says is I'm making a prediction of x at sample k plus 4, and I'm making the prediction at sample k. So that's a 4-step ahead prediction made at sample k. If you look at this other example over here, where I've got y k plus 6 k plus 2, this is a prediction of y at sample k plus 6, where the prediction was made at sample k plus 2. So again, this is a 4-step ahead prediction, but being implemented at sample k plus 2. So that's the common notation you will see in the literature, and that's used where you really need clarity to say this is a prediction variable, this is how far ahead I'm predicting, this is when I made the prediction. If we use that notation now with the general prediction we had before, this is what you get. If I write xk k plus n slash k, so that's the n step ahead prediction for x made at sample k, then that's given by a to the n xk. You'll notice there's no double subscript on the xk because the xk is not a prediction, it's a measurement, it's a known value at sample k. But then all the u's have got this double subscript, so ukk, uk plus 1k, uk plus n minus 2 slash k, and so on, because all of the u's essentially are decision variables. They're variables you have to decide what they want to be. What input am I going to use now? What input do I expect to use in one sample's time? What input do I expect to use in n samples' time? And so on. Similarly, you can substitute that in for the output, but I won't dwell on that detail. Now, the double subscript makes it clear where a value is notionally in the future or a predicted value or a decision variable, as opposed to something that you know. The double subscripts are used for clarity, but the key thing here is only where they're needed. You'll find quite often people don't put them in because they say it's obvious from the context what's a prediction and what's not. So if you don't need them, don't put them in. But if you think there's a possibility for confusion, then put them in. Next, what we want to do then is separate the predictions into the part which is known, so that's based on past or measured data, and the part which is yet to be determined, which will be based on the future inputs you haven't decided yet. Now that's relatively straightforward. If you look at this expression here for the n step ahead prediction of y, you'll see the bit I've just marked in blue is based upon known or measured data, and the bit I've just put red brackets around is based on the future inputs that you have yet to decide. So we have a known bit based on current and past measurement, and we have an unknown bit which is based on future input choices which remain to be decided, and that's quite a convenient way of expressing our predictions. And what we're going to be doing, obviously not quite yet, but in a few videos time, we'll be choosing the unknown, but use a different colour there, the unknown or the future inputs in order to make the prediction for yk plus n to do what it is we want it to do. So in summary, it's common to use discrete models for prediction, and this video has shown how state space models can be used to form n step ahead predictions. It's also shown that predictions can be separated into known parts based upon measurements and unknown parts based on decision variables that have yet to be selected. It was an implicit assumption here that the state is known, so we assume that xk was known. Of course, in practice, you'll probably have an observer in order to estimate this.